Okay. All right. Um, yeah, that's the end of the good news. So today we're going to start chapter 21. This is probably the most difficult stuff. So just fair warning, and not all of you I think will find it to be the hardest, but at least when I took organic 2, I was like, huh? That don't make no sense. The main thing I think that trips people up is that we're going to have multiple carbonyls reacting in different ways with each other. And there's like a couple different oxygen atoms that you're going to see and like which one does what. So we'll get to, actually, we won't get to that stuff today. So only one oxygen for today, but it starts to get a little complicated. Okay, so what we're going to do in this chapter is we need to have a way to talk about carbons relative to a carbonyl group. Okay, so we're going to use Greek letters to denote the carbonyl. So let's say we have this ketone, just something similar. The carbonyl carbon, the carbon double bonded to the oxygen, that one we just call the carbonyl carbon. But as we go outward from there, we're going to use Greek letters. So the carbon adjacent is going to be the alpha carbon. And then the beta carbon. And that's usually as far as we need to go, but just in case, gamma is next, and then finally delta. Epsilon, continuing, but generally speaking, alpha and beta are going to be the important ones. So the lower letters are closer to the carbonyl. Yep. This is delta. And this is beta. So the alpha carbons are directly next to the carbonyl. The beta carbons are next to the alpha carbon. And if you like, you can keep going, gamma and delta and such. So the chapter is called Alpha Carbon Chemistry. And so unsurprisingly, mostly we're going to focus on these carbons and the reactions that take place there. We've previously talked about reactions at the carbonyl carbon, like Grignard reactions and reductions and stuff like that. But we haven't talked at all about the other carbons next to the carbonyl. So get used to seeing the alpha like so. In addition, so that's the carbons, right? And so the alpha hydrogens are attached to the alpha carbon, beta hydrogens are on the beta carbon, etc. So if we have something like acetone, acetone has the two methyl groups next to the ketone. So what kind of hydrogens are these? Yep, these are all alpha hydrogens. If we have methyl tert butyl ketone like that, we only have alpha hydrogens on the methyl group on the left-hand side, but the tert butyl group on the right has no alpha hydrogens. Instead, each of the methyl groups, those are beta hydrogens. Oh my God. Seriously. Thank you. Okay. We have two very closely related functional groups that are going to be the basis for this chapter. And those are enols and enolates. Yes. So this one here, it's got hydrogens there and methyl groups here. These are all alpha. And those are all beta. Except
wait, why are they if they're on that alpha or
so here's the carbonyl carbon. So that's an alpha carbon because it's adjacent to the carbonyl carbon, and the hydrogens attached to it are alpha hydrogens. This is also an alpha carbon. It doesn't have any hydrogens on it. So on that side of the molecule, there's no alpha hydrogens. But there are three, well, I've drawn them out here, 1, 2, 3 beta carbons. And the hydrogens attached to those are beta hydrogens.
so if we see CH3s, we just include those are beta.
Not necessarily. It all has to do with the distance to the carbonyl. Yep. I think it'll make more sense when we do some actual reactions and stuff. So the two functional groups we're going to talk about, enols and enolates. I mean, they're really kind of the same thing. The word enol kind of sounds like en plus all, right? And so that kind of implies that it's an alkene plus an alcohol. And that happens to be the case. So enols and enolates are both going to start from a carbonyl compound. Should be down here. If we have a structure like this with an alkene and an alcohol attached to it, that's an enol. And an enolate is just the deprotonated form of an enol. So the way we get to these functional groups is starting from a carbonyl compound. So generally speaking, you're not going to start from an alkene to get to an enol or an enolate. Instead, you're going to start from a carbonyl. So to get to an enol, you need catalytic acid or base, and we're going to talk about that in more specifics in a moment. And to get to an enolate, you need a strong base. Now, often what's going to happen with enols and enolates is we're going to give them some other chemical to react with, quite a wide variety of things. And then what we end up with at the end of that reaction, actually, I'm not going to call it X. I'm going to call it Z, is attached to the alpha carbon of the ketone or the carbonyl. So we've regenerated our carbonyl. We have some group now attached to our alpha carbon. So in a reaction like this, we're going through the enol or enolate as an intermediate, but we're not actually isolating it. So enols and enolates are generally pretty unstable. They're just used as intermediates to get from one form, well, to get from one carbonyl compound to another. Also, you'll notice that I've drawn equilibrium arrows between the enol and the carbonyl and the carbonyl and the enolate. And so assuming you have catalytic acid or base, a ketone will go back and forth between ketone form and enol form. So let's talk about that in some more detail with some examples. So with acid or base, ketones exist in equilibrium with enols. So this is the same reaction that I just drew above. Now, you might be tempted to say that these are resonance structures of each other. Why is that not true?
Don't they not stop? And I just go back to the console.
Yeah, but resonant. Well, it is true that resonance structures are different ways of describing the same molecule, and these are different molecules. But the main thing is we've moved atoms around. There's now a hydrogen on the oxygen. And so if you have any sort of different arrangement of atoms, you cannot have resonance structures. So we call these tautomers. And so the process of going back between back and forth between the two is called tautomerization. It is kind of a funny word. Okay, so we need to talk about the mechanism because this is important. For acid catalyzed tautomerization between the ketone and the enol, so we call that keto-enol tautomerization. Say that 10 times fast. And we'll also talk about base catalyzed, but don't worry too much. There's only a couple of steps. So we start with our ketone, and it's acid catalyzed. So we've got some acid in solution. And in this case, I'm going to use the hydronium ion, which is H3O plus, or like this. And the first step we do is we're going to protonate. We're going to protonate the oxygen of the ketone. So we haven't broken the CO double bond. Yes. Come on, there we go. So we haven't broken the CO double bond, but we're gonna do that now. So we can draw a resonance structure of this molecule just by moving electrons up onto the oxygen. So that now gives us a positive charge on that carbon, the carbonyl carbon, and a neutral oxygen. And now it's also important to note that we have an alpha hydrogen. So on that carbon, there's a hydrogen. Actually, there's three, so should maybe draw those out. And if we have molecule of water hanging around, which we do because at the beginning we used H3O plus hydronium and we deprotonated that, so that leaves us with water. Our water is going to deprotonate the alpha carbon. And those electrons are going to go to make a double bond between those carbons. Yep. And there we have our enol. Questions on that little mechanism? So all that's happening here really is proton transfers. So we're transferring a proton from hydronium to the carbonyl. Then we draw a resonance structure, and then we transfer a proton away from the alpha carbon, and we make a double bond between those two carbons. Okay, so that's acid catalyzed. We can also do this under basic conditions. In this case, so let's see here. In the acid catalyzed mechanism, first we protonate the ketone, and then we deprotonate the alpha carbon. Yes.
So, previous method, you say it's like a little bit more complicated, there's like nitrogen,
Mhm.
that the group is. Would you still be able to do the reaction or no?
A nitrogen.
Like, if it
Um, so like if one of these was a nitrogen,
was done or no?
you would probably get a different reaction in that case. But I'm not going to give you an example like that. Yep. Okay, so for the base catalyzed example, we're going to flip the order of doing things. So first, we're going to deprotonate the alpha carbon. So in order to do that, we have to show our alpha hydrogens, or at least one of them, but I'll show all three. And let's say that our base is hydroxide. So to deprotonate, we just grab a hydrogen there. And rather than moving the electrons toward this bond, which would cause an issue with this carbon, give it too many bonds, we're just going to make an anion on the alpha carbon. So the electrons are just going to go right to that carbon. Okay, and as we did in the acid catalyzed mechanism, we can draw a resonance structure of this. And we'll just do that by swinging these electrons there, and then moving the carbonyl electrons up onto the oxygen. So look, it looks different. And the reason it looks so much different is because we're under basic conditions. So we have OH minus. And when you're under basic conditions, you want to make sure you don't draw, or at least try to avoid drawing positive charges on your organic molecules. And in the same way, when you're drawing an acid catalyzed mechanism or you're under acidic conditions, you want to avoid drawing a negative charge on your organic molecules. So now we've got an O minus, and so we can do the first step of the acid catalyzed mechanism, second in the base catalyzed mechanism, and that is to protonate it's not really the ketone oxygen anymore, but you get the idea. It's still this oxygen atom. Come on. And we've made water here from our hydroxide. Like that. And so we protonate using that hydrogen from the water. And there we have our enol. So same starting material, acetone, acetone. I've just drawn out the hydrogens explicitly. And same product, enol and enol.
And the, either the water or
Connect the water. Yeah, water is going to be involved in the last step of both of them. Mhm. So we don't really have time to work through this right now, but use this molecule to do both acid and base catalyzed tautomerization reactions. But remember that because we have a benzene ring here, this carbon does not have any hydrogens on it. So there's no alpha hydrogen on this side, but there is an alpha hydrogen over there. which is okay if you sort of follow this mechanism because I've drawn everything on the right-hand side. So you can do the same for that practice example. Okay, so that was enols. Arguably more important are the anions of enols, which are enolates. So if, and this is going to look like the same thing I just drew, but it is a little bit different for one specific reason. So if we take acetone again with its alpha hydrogens, and we treat it with a strong base, so something that's stronger than sodium hydroxide. Okay, that should be equilibrium. We do the same reaction. And now you're going to say, oh, okay, so what do we do here? This looks just like the base catalyzed mechanism, right? Deprotonate, draw a resonance structure, get to here, and then you protonate it with water. But if we're using a really, really strong base, we're not going to have any water in solution. So kind of a caveat here that there shouldn't be any water around. Then once you treat your ketone with the strong base, it's just going to stop right here. So this is relatively stable because it's resonance stabilized, right? And then this also means that, well, I said it's stabilized, but of course it's still quite a reactive molecule. And because of the resonance structures, it's got two reactive sites. The first is this resonance structure. And so I'm going to omit the hydrogens and just draw the lone pair on carbon. So here, our enolate is nucleophilic at the carbon. And we have the resonance structure of our enolate, where the negative charge is up on the oxygen. And unsurprisingly, here, the enolate is nucleophilic at oxygen. Based on your knowledge of electronegativity trends, which of these is a stronger nucleophile, carbon or oxygen? So in order for something to be a stronger nucleophile, that means it's a more reactive molecule. More reactive molecules are generally less stable. So another way of asking that is, which of these is less stable? Having a negative charge on a carbon or having a negative charge on an oxygen? Less stable. Carbon. Oxygen's more electronegative, so it's more okay with that negative charge. That means that this molecule is a bit more stable, this resonance structure, same molecule. This resonance structure is lower in energy. This one is higher in energy, so this one is more reactive. So an enolate is most likely going to react at the alpha carbon. I mean, I did say this was alpha carbon chemistry, but anyway. So when you see an enolate, this structure looks nicer because you've got the negative charge on the oxygen, and that feels good. At least to me, it does. But this is going to be more reactive, and so you're going to see reactions take place at that carbon instead.
Question.
Yes.
The one on the left. When you store it, would you have to store it differently because it's more reactive? Or no?
You don't store it. You make it in your reaction flask and then immediately add the next thing. Yeah, you can't store these.
It's limited to these ones.
Yes,
That's very good.
correct.
Most things.
Right. That also means that this is the better resonance structure because it's more stable. And so if you were to, I don't know, take a picture of the molecules, I know you know that this is not how it works, but this is a greater resonance contributor, but this is the more reactive position. Okay. Okay, so I said that you want to use a strong base for this with no water. So you can't use sodium hydroxide. First of all, it's not strong enough. And second of all, most of the time you're going to have some water with your sodium hydroxide. Usually it's as a solution in water. So we need some other kinds of bases in order to form enolates. Okay, so as I said, water bad. So water will destroy the enolate. And it just gives you the enol back. I need to turn off that thing. So because of that, we want a base that doesn't necessarily rely on water, and more importantly, doesn't pick up a proton to become water. Okay, so I'll show you kind of what that means. So we're going to use either sodium hydride or a new base called LDA. I'll show you the structure in a second. So we're going to use sodium hydride or LDA. Not sodium hydroxide, potassium hydroxide, you know, whatever hydroxide based base you happen to have. So let's look at sodium hydride first. Sodium hydride is Na plus, and hydride is H minus. So this is a stronger base than sodium hydroxide, and It has a very convenient property, which we're about to see. Okay, so we can draw the mechanism here, kind of just like we would for the acid and base catalyze things above, except this isn't catalytic, as we'll see in a moment. So we deprotonate, grab that hydrogen, electrons move onto the carbon, and that forms our enolate. What else is formed in this reaction, just based on the arrows? Yeah, so the enolate is really a salt with a sodium cation. What else? I think I heard it. So no, the sodium and the hydrogen are not connected. Instead, the sodium is going to go with the enolate, but this hydrogen has moved its electrons to form a bond with that hydrogen, and this hydrogen, that bond is broken. So what's that molecule? H2. What do we know about H2? What are its physical properties? Solid, liquid, gas? Gas. So when you have a solution of your enolate, you treat it with sodium hydride, you get bubbles of hydrogen gas that come out of the reaction. That hydrogen is gone, and so this is not a reversible reaction, not an equilibrium reaction, unless you were to, I don't know, do it in a pressure vessel or something extremely stupid like that. But the fact that we generate hydrogen gas is the driving force for this reaction. Yes. Yes, that's a slash, sorry. Okay, so that's sodium hydride. Yeah. Enolate? Yeah.
I thought that the enolate was a double bond, a single bond at oxygen. But there,
It's both. So it's either of these two resonance structures. So I've drawn this one. You can draw that one also. Yep. Okay, let's look at LDA, this mysterious compound that I have not told you about. So it's going to start the same way. We have, in this case, our acetone. But LDA stands for lithium diisopropyl amide, which interestingly enough does not have an amide functional group in the way that we've talked about it in the last chapter. So LDA is that. Amide is also a word for a nitrogen with a minus charge, which is really unfortunate because it's also the name of an organic functional group. Anyway, so, but this is a base, just like any other base. It's got a lone pair, in this case, two lone pairs with a negative charge, just like the hydride has a lone pair with a negative charge. And so we're just going to do the exact same thing here. Yes. Yes, lithium. Yeah. Now, here we have the hydrogen bubbling out. That's our driving force for that reaction. For this one, it's that this molecule is really stable. The isopropylamine, it's got a pKa of 36. And so even this enolate is not going to be able to pull that hydrogen away from the nitrogen. So that molecule, very, very stable. In fact, this hydrogen is attached more strongly to the nitrogen than this carbon is attached to that hydrogen. That's why this reaction is able to go forward. I think the pKa of acetone is, I don't know. Probably should know that, but yeah, favorable reaction, also essentially irreversible. No, this is just formation of the enolates. So you can kind of make an enolate with a weaker base, but it's going to be an equilibrium reaction because you're going to make water and all that stuff. So if you actually want to do enolate chemistry, like we're going to be doing, you really need a stronger base like this. Now, that being said, when we do the aldol reaction in lab, we're going to use sodium hydroxide because you only need a small amount to get that to work, but we'll get there in a bit. Okay, so as practice, should be able to figure out what the product of that reaction is. Okay, another sort of exception where it's okay to use a weaker base is in the case of beta diketones. So hang on, I'll draw it in a second, but beta diketones are very acidic, and acidic means easy to deprotonate. So if we have a molecule like this, where we have two ketones separated by one carbon, the reason these are called beta diketones is because relative to this carbonyl, that's the alpha position, and that's the beta position. So the ketones are beta to each other. So the reason that these are very acidic, specifically they're acidic at those hydrogens, that's because, and here I'm going to use a fairly, I mean, yes, sodium hydroxide is a strong base in general chemistry, but here it's quite weak compared to the other bases we're using. When we do this, we're left with that anion. And previously we did drawing of resonance structures of these, of like an enolate type thing. And so because we've got two carbonyl groups, you've got two different directions you can draw that resonance structure. So these are like doubly resonance stabilized.
And you said this was an exception?
Yes, because you can, for acetone, you need a really strong base like LDA or sodium hydride to get the enolate. But for, this is called acetoacetone, ACAC, you can just use sodium hydroxide. And this molecule with the negative charge is stable enough that that reaction will work. Okay, all we've talked about is like making various forms of the same molecule, and that's fantastic, but we should do some reactions. So our first one we'll talk about is a fairly simple one, and that is alpha halogenation. So what do you think happens in this reaction? We put a halogen where? The alpha position. Yeah. So if we have acetone, we react that with elemental bromine. This doesn't look like it will do anything. And it won't until you add some acid catalyst. So we're going to get a bromine installed at the alpha position. Now, when you're counting alpha, beta, etc., make sure you don't say, okay, this carbon is the carbonyl carbon, this carbon is the alpha carbon, so the bromine is next to the alpha carbon, so it's beta. It doesn't work like that. In this case, we're treating the bromine like it's a hydrogen, where we're more concerned about the carbon that it's attached to, which is the alpha carbon, just like the one on the other side. So the bromine is alpha, or at the alpha carbon. Side product here is HBr. Okay, so another mechanism, but fortunately we've already done half of the mechanism. Okay. So part one is acid catalyzed enol formation. So we know how to do that. We start with our carbonyl. We have H3O plus, our acid. The first step is to protonate the oxygen of the ketone, and we do that like that. Maybe I should make it less ugly. So there's our protonated ketone. We draw a resonance structure. Of the ketone that looks like this. Nope, not done yet. Need a hydrogen. Sorry. So we draw a resonance structure of the ketone, and then we deprotonate the alpha carbon. And we can do that just with water. And here, because we've got that positive charge, we can draw the electrons to form a double bond. Okay. So that should be exactly identical to what we just did before. Part 2 is the actual halogenation. So we get to start from the enol. And our halogen source is just Br2 bromine. So it looks like that. And I said that the enol or the enolate, either one, is nucleophilic at the alpha carbon right there. It doesn't really look like it, but that's a nucleophilic site. And so in order to form a bond between the nucleophile and the electrophile, which in this case is the bromine, we're going to move one of the oxygen lone pairs down to form a double bond. So this is remaking our ketone in a way. And at the same time, our nucleophile is going to reach out and grab the bromine. And it's going to do that with the electrons from that double bond. So we're going to make a bond between the alpha carbon and the bromine. Also, bit accessory to everything else, but still important. We have to break the bromine-bromine bond, so we don't have more than an octet of electrons on the bromine. Okay. So what does that look like? Well, we've got a double bond to the oxygen, still attached to that hydrogen. So that oxygen has a positive charge. And we've made a bond from that carbon to the bromine. And we've got a Br minus. Now all we have to do is, if you're not kind of sure where we're going, look back at the expected products of the reaction. So we're going to get the ketone with bromine at the alpha position. We've got the ketone with the bromine at the alpha position. We just need that hydrogen to be gone. And HBr is another product. Well, we have the Br minus, and we've got an H that needs to go away. So let's use the bromide, the Br minus, to deprotonate our protonated ketone. Like that. And there we go. So. First, we form an enol, protonate, draw a resonance structure, deprotonate to get your enol. And then we do halogenation. We use the nucleophilic carbon with its pi bond to make a bond to the electrophilic bromine. And then that's the main step really of the reaction. And then all we have to do is deprotonate the carbonyl. So I'll give you a bit of practice for this one. Tip here. When you're going to form the enol in the first half of the mechanism, you'll have two options. You can either have the double bond go to the left or to the right. And because more substituted carbon-carbon double bonds are more stable, you're going to want to form the most substituted CC double bond. Okay, I mentioned this very briefly in passing. But this is really important, something to keep in mind as you're drawing mechanisms. Never draw a strong base under acidic conditions. This is something you should have learned in Chem 1, but I'm not making any assumptions. Never draw a strong base under acidic conditions. So for example, that would be something like something with an O minus, and acidic conditions might be something like H3O plus, right? You should never have these two things present in a mechanism at the same time. And unsurprisingly, you should also never draw a strong acid under basic conditions. So basic conditions might be OH minus, and a strong acid could be, well, something like we've seen in this chapter, an oxygen with a positive charge, like a protonated ketone. Questions from today? All right, how do we, yes,
The answer key for. Oh, wait, we haven't.
you haven't turned it in yet, but yes, I will, yes. Yeah, how do we feel about this? Okay, that's fine. That's good at this point. All right, see you on Thursday.